done this. And so if there's any glitches, I apologize, but just let me know in the chat if anything goes wrong. But it looks like everything's good on my end from what I could tell. So yeah. So like I said, it's been a while. So I'm happy to be back. It's nice to be able to have this opportunity to like explain stuff in just a little bit of a different setting and maybe from a different perspective. So this is the Unit 5 review for energy. And so we're going to start just with a little bit. Well, first of all, the thumbnail, if you clicked on this before I started, was kind of wild. It's not like, if you go back and look at some of my other videos, it's a little different because I'm like, I'll just have AI generate something. And so it tried to do a Steelman. So I guess that's what a Steelman looks like in AI world. But yeah, oh well. So yeah. These equations, first of all, I just general tip here for physics. The equations are your friend. Let me just see if I could put this up, if it's going to work. Last time I tried this, when I was testing this out, it kind of crashed on me. But if I could put up the equation sheet, you should just have yours out. Okay, not working. That's okay, I'll just drag it over here. So these are the equations that you'll be using, that you've been using. And my suggestion to you is make sure that you are familiar with them. Like literally, and I'm just gonna take this away so I can look at the PowerPoint again. But like, we're gonna start with these first three. Be able to say them out loud to yourself. You know what I mean? Like, what do those letters mean? What is work? What is W? It's work. What is F? It's force. What is D? It's displacement. And so on. So P is power. And just by reminding yourself what those letters mean, it's going to really help you tremendously with all these things that we're going to be talking about and what you're going to be tested on very soon. So what I'd like to do with these review live streams, from just what I've heard in the past, what people want is just, what students want is just a little bit of more explanation, I guess. Not just me just talking, but like this, like an example. And so as I go through this, what I'm going to suggest you do is, if you're watching live, you can go as fast as you can if you want to, or you can really pause it. I mean, it's cool if you do that. If you find one you really want to try out, pause it, okay? And then you could catch up if you want to, or just watch a slightly delayed version of this. And if you're watching not live, well, it's way easier. Just pause it and wait as long as you can to solve these things. It's going to help you a lot. Okay. I'm getting sort of a warning here, but we shall see as it's working. It seems to be working. Again, it's been a couple years since, so I apologize about this. I'm not sure what's going on, but it seems to be working. So I will, unless I hear from you otherwise, I'm going to continue on as if it's okay. So yeah, it's good. All right, so here we have first question. We have a 10 kilogram box lifted from the floor up to the shelf 2 meters high. Approximately how much work was done on the box? So like I said, if you are familiar with these equations, that's going to help you. It wants to know how much work was done on the box. Well, there's two ways you can go about this. The very first equation is force times distance. But then there's the last equation where work is also delta E, the change in energy. And so in this case, it's not giving us anything about energy, but it is giving us, well, it's giving us mass and it's giving us distance. Now I bring this one up because this is a really popular one to get wrong, okay? A lot of students will choose B, okay? This is a very common wrong answer because you say, well, work is force times displacement, right? And doesn't that mean 10 times 2? That's 20, right? No, because if you, like, this is another thing I would suggest you do is pay attention to those units. That's mass, that's kilograms. The meters is fine, that's definitely distance, but that is not force, okay? You'll see this sometimes. You just got to remember the force. Whoa, what is that P for momentum? I don't know. The force of gravity is mass times gravity. So what that means is you actually had to take that 10 kilograms, and I'm starting right, like I would call this more of an intermediate question, right? Because I didn't give you force. I gave you meters, but I didn't give you force directly. So that's force times 9.8 meters per second squared. And so the actual force is going to be 98 newtons is what it ends up being. And so that is your force that you have to multiply. Okay, so watch out for that. Like really pay attention to the units that are given. This is kilograms. So when I take the force, which is 98 newtons, and I multiply it by the displacement, 2 meters, then I get about 200. So the choice is going to be C. All right, big difference. And again, that's kind of important. So just like watch out for that. Okay. I apologize if I keep like scrunching my face. I keep getting a warning saying that it's not working well. So I'll stop scrunching my face. All right, so hopefully you get that. Like I said, the big takeaway is don't just blindly multiply numbers together. Like this one's almost too easy. Like some of them are going to be easy, but like just kind of like put up a little bit of a filter. Like, hey, wait, that's kg. Force is newtons. All right. All right. So while I'm going through this, I will just point out, I've got my phone open. I've got the obviously YouTube chat. So if you do have any questions about anything, just let me know. I will gladly help you out. All right. So moving on, because I do want to, this is honors. Yes, it is. This is honors unit 5 for our test on Monday, right? So it is. By the way, there is a delay, so I answered that maybe before even the question popped up on your screen. So it is. So here we go. Here, just to be sure. All right. So the next question I have for you to kind of think about a little bit. Again, pause it if you need to. Look over something. Which of these is the greatest rate of power? All right. So power, that is. There it is. Let's not put it there. Power is work divided by time. It's also the change in energy over time. So that's something to keep in mind. Work over time is going to be basically the same thing because change in energy is work. Work in physics, the idea of work is when something either adds energy or takes energy away. Okay. In other words, the change in energy. So whenever you see work, just remember that it's either taking energy away or adding energy to it. Okay, so that's power. So what we got to do for a situation like this, when we have 3 scenarios and we need to figure out which one is the greatest, we should probably figure them all out. Okay, so we're going to keep this equation in mind. Work, if you remember, is, we just did this, force times displacement. So we can just kind of like replace the W, the work, with force times displacement as we do these questions. So in this case, it's going to be the force. All right, I screwed that one up. How do I? Where's my little thingy? Okay, let's do this. I want to erase this. Is it going to let me? No, I got to do it the old way. There we go. Eraser. So let's just erase those. Come here. All right. So what we want to do then is, like I said, we want to multiply force times displacement and divide it by the time to figure all this out. So force is 15 newtons. The displacement is pushing a box over 15 meters, so 15 meters. And going to be dividing by 5. So that's going to end up to be, when I put that in my calculator, 45, it's going to be watts for the power. Okay, so we'll compare that to this one, lifting 20 newtons. So there's my force. This one is nice because it actually gives it to you. For 10 meters, so there's my force and displacement. Again, I'm just kind of using how power is equal to force times displacement. Okay, and divided by time. and divide that by 10 seconds. So this should be seconds over here as well. So for that, when you put that one in your calculator, you get 20 watts. So far, letter A is winning. So it won't be B. Boink. Okay. Pulling a box with 30 newtons for 5 meters over 5 seconds. Again, there's a lot of letters there, a lot of numbers and everything. So maybe what you can do is just like on a scratch sheet of paper or something when you're working through this, say, okay, this is force, this is my displacement, and this is time. And then what that does is now you look at the equation, which again should be right in front of you because of the equation sheet, and you almost barely had to think about it. There's force and distance and time. So if I take that force of 30 newtons times the displacement, 5 meters, and I divide it by the 5 seconds, well, for that one, I believe when I put that in my calculator, yeah, the 5s will cancel out, and I'm left with 30 watts. Well, 45 is still bigger. So that means, where'd my little pen go? There it is. That means C is not the answer. And so far A is still the best. So see what I'm doing here? I'm kind of just going through and I'm figuring each one out. Now, do you have to write all these out? Can you just do it in a calculator? Sure, if you feel comfortable doing that. I am writing it down because I know I am prone to making mistakes. Right now, I'm slightly nervous for being on YouTube live in front of whoever wants to watch this. You might be nervous because you're taking a test and you know it's a big part of your grade. So you might be nervous for a different reason. So maybe writing it down will help focus you a little bit. Now here's an interesting question. It says you're just holding the ball, right? So look out for words like that, holding the ball. What is the distance it's moving? What is the displacement? The displacement is 0. Well, I don't have to go any further, but I could put it here 20 seconds because that's going to equal 0 watts. Okay. So D is not, where did it go? There, D is not the answer. So that means A is my answer for that one. Okay. So you see how what I did there, I just compared them all. You do have to work it all out. And sometimes that's just how it goes. Okay. But by working it out, you know you got the correct answer because like I would have glanced at this and maybe ooh, 80, that's a big number. And I'd be like, well, it's holding. So I know that that's not gonna be right. There's like 30 is a big number. Is that gonna be right? Like, how could it be this 15? That's like one of the smallest numbers there. Just like work it out and then you'll know for sure. All right. So we're still talking about work and energy here. We got a kid standing on top of a 19-meter hill. They have 10,536 joules of energy, potential energy. How much work did he do to get to the top of the hill? Once again, you might be thinking, work. Work is force times displacement. Cool. So, well, there's my displacement. That 19 is like a displacement right there, right? Force, well, it's not given. Well, maybe it's this 10,000, right? Is that force? Ooh, wait. Okay, right now, this is why looking at and being very familiar with these units should be something that you prioritize because looking at that's not force. Force is in newtons. So what do we do here? It wants how much work. Oh, wait, there's another equation on the equation sheet. Don't forget this one. Work is also the change in energy. Okay, how much energy did this kid do to, how much did the kid's energy change? Well, they did the work already, right? They did it. It's done. Past tense. How much work did he do? So how much did he do? Like he's not just standing there, right? He is standing there, but he already did the work. So how much work did he do? Well, this joules, this right here, joules is energy. So the kid had to have done 10,536 joules of work in order to gain that much energy. So the answer in our case is B. Okay. So that's how it is. Okay. So if you had gotten A, it's probably because you multiplied 19 times 10,536. That's just blindly multiplying things together. You don't want to do that. Okay, so take a moment. Again, practicing this and being familiar with the letters and what everything means will be really helpful to you. Okay, which of the following are true about energy? Well, this is a definition question, right? Is energy the ability to do work? Yeah, if you Google or look up the definition of energy, this is probably what it's gonna tell you, something about the ability to do work. That's like the definition of energy, classic definition. I don't like it that much, but that's what it is. It can slow something down. Ooh, now we're getting closer to what I think of as a more useful definition of energy. Energy is, well, it's the ability to cause change in something, I like to say, like to do something or to make something be done, or in this case, to make something slow down and stop happening. It's causing change, right? It could cause an acceleration. Well, that's also the definition of like slowing down or speeding up. It always causes an acceleration. Energy causes an acceleration. Well, yeah, I mean, energy can cause an acceleration, I guess, but I don't know if it, like, you can have energy and not accelerate. Like, if you're just at the top of a hill, you're not accelerating, right? Okay, can cause, it always causes an acceleration. That's a key word. So I don't know if it always causes an acceleration. It doesn't. It doesn't have to. It can cause, though. All right. So anyway, letters E, it can result in a constant speed. Well, that's what I was just saying. Like, you can have a constant velocity. That's, yeah, you have energy. It can be stored. Energy can be stored, yes. It can change forms. Yeah, energy cannot be created or destroyed, but it can change forms. So there you go. All right. The 500 Newton, okay, look at this little diagram here. A 500 Newton block is pushed up a 3-meter ramp that is 25 degrees from the ground. So that is in the truck, 1.2 meters off the ground. How much work was done against gravity to get this to the top? Yikes. Well, there's a lot of numbers there. There's angles there. What's up with this angle here? What's up with this angle here? I don't know what was going on with that. We'll ignore that. It doesn't matter. Okay, this is like the stair lab you did, where you walked up the stairs. Remember, the direction you had to push the most, because gravity was, you pushed down and the stairs pushed you up. So it's vertical. So all we need to really worry about is the vertical distance, because that's really the hard part. Moving something sideways doesn't, I mean, there's friction involved, but we like to ignore friction. But the hard part is moving against gravity. So that 1.2 meters is really the important part of this. And so our answer here is going to be A. Literally, it's just force times displacement. The box has a weight of 500 newtons, which means that that's how much you had to push. That's how much the box had to be lifted straight up. And it moved 1.2 meters. There should be meters after that for all of these. Units should be involved. But that's it. So don't overcomplicate it. Just remember definitions and you should be good. Just remember the equation and what it is. So, all right. Which of these is not considered work? Not considered work. A car using its brakes to slow to a stop. Well, that's cool. That's fine. It's causing a change. That's actually negative work. It's removing energy from the system. Okay, so that's, wait, not considered work. No, cancel that. I don't remember. There's a button I could press for erasing. I don't remember it because I haven't done this in a while. So let me just do that. That is not the correct answer. All right. I had to manually change things. I apologize. The wind blowing a plastic bag around your neighborhood. Well, okay. Yeah, that's positive work. It's actually like adding energy. The wind is. Carrying your backpack up the stairs on your back. Well, that's also work. You are moving something over a distance. Holding the phone in your hand. Holding. Is there a displacement involved with that? No. So that is not work. Okay. No matter how heavy your phone or whatever object is, if you are not moving, there's no work being done. All right. And that's basically it for the first part of the unit. The second part, we moved on to the different types of energy. And again, I'm going to repeat myself here. Familiarize yourself with these equations, all right? And the way you do that is practice. You have to do the practices. I will say this, for whatever reason, I was looking back at previous tests, and I mentioned this a while ago, but I'm going to say it again. For some reason, not a lot, but enough that is like, what? Enough that stood out to me. Some students tend to forget to square things. They forget to square it, and like that will cost you. So don't make dumb mistakes. You know, I've definitely seen enough of you guys understand the physics. You understand the equation. You understand what you need to do, and then you make a dumb mistake. Well, we all do that. It's very, very normal to do that. Making what I call a dumb mistake, you know, like you either put it in your calculator wrong, you forget how to put it in your calculator, you forget a number, you forget a squaring it. But yeah, so more practice is going to help you with that, okay? So remember that. Remind yourself to square the displacement when you're dealing with elastic potential energy, and remember to square the velocity when you're dealing with kinetic energy. All right. Okay, so a couple questions about that. What can be changed in order to directly affect the kinetic energy of an object? Well, looking at the equations, that's going to be very helpful for these types of questions. So what is kinetic energy? Here's kinetic energy. And so what can be changed? Well, you can change mass and you could change velocity. Okay, so that's going to be my choices. I could change the mass. No, and I could change velocity. Okay, that just has to do with looking at the equation. So kinetic energy is 1/2 mass times velocity squared. What can be changed in order to directly affect the gravitational potential energy of an object? All right, gravitational potential energy is mass times gravity times height. So you can, again, change the mass of something. You can change its height, not the spring constant, not the velocity, and displacement. Not to muddy the waters a little bit, but it depends what is the displacement. If you're talking a vertical displacement, like in the y direction, then yes. If you're talking about just displacement like along the x-axis, like horizontally, then no. Okay, we've been referring to it as height, so that's how it's going to be. All right, but I'm just saying, like, you can argue displacement as long as you're talking vertical. Okay, a car triples its speed from 10 miles per hour to 30 miles per hour. What happens to its kinetic energy? And we got all these choices here. What do we do with this? Is it going to be a triple? 3 times because it goes from 10 to 30? That's the wrong answer. Okay, so it's not going to be B. Why not? What is it going to be? Well, kinetic energy, right? Kinetic energy is 1/2 mass times velocity squared. Okay, see where I'm going with this? Mass doesn't change, so we could pretty much just ignore that. But looking at velocity, velocity is squared. We're going from 10 to 30. That's 3 times the velocity. So if I take 3 times the velocity and I square that, that's going to give me 9 times the velocity. So it's going to be 9 times what it was. Got it? So, okay. So it's just that square that really affects things. Velocity is like that. And again, this is a review, so I'm going kind of fast. But let me know if you got any questions. So a car of mass m and a truck of mass 2m are driving next to each other at 50 miles per hour. What can be said about the kinetic energy of each vehicle? Okay, it doesn't give us like actual masses. It just says basically the car is a certain mass and the truck has twice the mass. That's what it's saying. So if the car was 1 ton, the truck is 2 tons. You see what I mean? So the mass is doubled. Kinetic energy. So kinetic energy is 1/2 the mass times velocity squared. All right, so what are we doing? we're looking at the mass. We just doubled the mass. We have twice the mass. And so that means it's going to have twice the energy. Okay. It is not going to have 4 times the energy because we are not squaring the mass. We're just doubling it. Or not even, I'm sorry, we're just, it's just by itself there. All right. Half of the mass, no matter what. They're both going the same speed. So same velocity. Okay. So do you see the difference between the previous question and this one? The previous question was asking about velocity, and since velocity is squared, then any changes to velocity is going to have an exponential effect. Any changes to mass is going to have a linear effect. It's going to have a proportional effect. So whatever happens to the mass, it's going to have a proportion. If you have half the mass, you're going to have half the energy. If you have twice the mass, you'll have twice the energy. Okay? All right. A car of mass m going 2 times the velocity speed, 2v speed, passes another car of mass m going v speed. What can be said about the kinetic energy of each vehicle? Now, all this is saying is the 2 cars have the same mass. Okay, so mass m and mass m. I don't know what they are. A ton? We'll say a ton. It makes it easier. 1 ton. All right. And it's saying that one car is going 2v, 2 times some velocity, and the other car is going 1v. In other words, all this is saying is the first car is going twice as fast. That's it. So it's going twice as fast. So reading that, if it's going twice as fast, like we've already discussed, it doesn't have the same energy as the slower car. That doesn't make any sense. The faster car has twice the energy. We just talked about that. Velocity has an exponential effect. The faster car has 4 times the amount of energy as the slower car. Well, it's going twice as fast. So it's going twice as fast. And if you square that, that means it's going to be going 4 times as much energy. So the answer has got to be C. Half, no. 1/4, no. So again, that's going back to the fact that velocity is squared. All right. Again, if you got a question, this might be something you need to look over, but it all goes back to that equation. Speaking of equations, you might see a question like this. We have dealt with graphs a lot before. It's been pretty rare where we have one that looks like completely blank like this. But what this is saying is that the y-axis is whatever is here, and the x-axis is the second thing, right? So whenever you have a graph, it's just like, let me just show you. Kinetic energy versus mass. Okay, kinetic energy versus mass. If you look at the kinetic energy equation, which we just got done talking about, 1/2 the mass times velocity squared. It's a proportional relationship, kinetic energy and half the mass. Okay, there's no squaring involved. There's no square roots involved with mass. It's half that's a proportional relationship. So that means that letter A is going to go with graph 1. In other words, as kinetic energy goes up, mass goes up. And I guess the other way around. As mass goes up, kinetic energy is going to go up linearly, proportionally, the same amount. Okay. Letter B, kinetic energy versus speed. All right, well, speed is an exponent. So what that means is we're going to have an exponential relationship, which means that, and it's not going down, it's not going like these last two, it's going up. In other words, as kinetic energy goes up, I apologize, as speed goes up, kinetic energy is going to go up exponentially. So this will be B, okay? Because it's an exponential relationship. Letter C, gravitational potential energy versus mass. Okay, well, let's look at that equation. Mass times gravity times height. Those are all linear relationship. Nothing is squared. That's kind of nice. So if you increase one thing, then potential energy is going to go up linearly, the same amount. It's going to go up proportionally, which means that graph number 1 is C. Okay, as mass goes up, gravitational potential energy will go up proportionally in a linear relationship. Letter D, gravitational potential energy versus height. Well, once again, it's not being squared or anything. It looks just like it has the same relationship as mass. And so letter D will be graph number 1 again. Letter E, potential energy, elastic versus the spring constant. Let's write this over here again. Elastic energy is 1/2, you look at your equation sheet, kd squared, k times displacement squared. Well, spring constant, that's this k, that's the spring constant. There's no squares on there, so that's what we call a linear relationship again, and so that will be letter E. It'll be graph number 1 again. As the spring constant increases, the elastic potential energy that's stored in that spring will go up proportionally. All right, there's no squares involved, it's a straight number. Displacement, potential energy, elastic versus displacement. Okay, well, here's another one that's squared. And a squared relationship looks like graph number 2. So that will be also F. As displacement increases, elastic potential energy will increase exponentially. Okay. Yeah, this might be neat, one slide you need to come back to and look it over again and hear my explanation, or you could ask me. All right, let's see here. Which of these springs is the most difficult to stretch? A, spring A because it has the lowest slope. B, spring A because it has the highest slope. And then so on. Spring B because it has the lowest slope. Spring B because it has the highest slope. Both are the same because this could be a choice. Yeah, this should be a choice. I don't know. E should be a choice. Yeah, I couldn't think of something else to say there. So the question is, first of all, we know, okay, which one has the higher slope? Graph A has the higher slope. So we know that it's not going to be choice A. We know that, let's see, spring B, it does not, spring B has the lowest slope. So it's not going to be D. It's not going to be E either. So which one is it? Well, more difficult to stretch. This is really simple. The higher the slope, the harder it is to stretch. So the answer is B. All right. So in other words, the farther you stretch it or extend it, the farther you stretch it, the more force it's going to take. Okay. My y-axis is force. My x-axis is extension or distance, displacement. So the more force you apply, the farther it will be stretched or extended. That's basically what it comes down to. What is that? That's the spring constant, okay? So slope of a force versus displacement graph is the spring constant. I'm pretty sure that's in the notes somewhere, but there it is again. So the slope of a force versus displacement graph is the spring constant. Something to keep in mind. Spring constant is just a measurement of how stretchy it is. Which of these springs has the higher K value? What? K value is just another way of saying the spring constant. So spring constant. All right, well, what do we just say? The higher spring constant is the higher slope. So which one has the higher slope? Letter A. Spring A, choice B. Okay. So higher slope means higher spring constant, means it's more difficult to stretch. All right. How much energy does it take to stretch the spring 0.2 meters? Energy. In the previous question, we were talking about slope and forces and stuff like that, but there was no mention of energy. Whenever you see energy mentioned and you have a force versus displacement graph, you had to find the area. Okay, under the line, you have to find the area. And remember, don't find the area of the entire thing. We just want to go up to 0.2 meters. So I need to find the area of, whoa, I could draw a straight line, not very easily. I need to find the area of this triangle here, okay, up to 0.2. And I think it's on the equation sheet, but if you can't remember, area of a triangle is, and then I've seen this many ways, 1/2 base times height I've seen, or I've seen it as base times height divided by 2, which is the exact same thing. So the bottom line is my area here, the base is 0.2 meters. That's the base. The height at that point, it looks like it's 6 newtons. 6 newtons divided by 2. And so when I put that in my calculator, I get 0.6 joules. Okay, so that's how you do it. Area is to find the energy in a graph, you must find the area, okay, for a spring. Got it? Force times displacement. What is the K value of this spring? What? Wait a minute. Well, what did we say earlier? Let's go back a couple slides. Slope is the spring constant. Slope is the K value. Same thing. So what is the K value? What do we got to do? We've got to find slope. Now here's where some of you guys are making mistakes. And it's an honest mistake, but I'm going to show you how to do this better. Keeping in mind that if you apply 0 force to a spring, it's going to be stretched 0 meters, right? So all these graphs should go through 0, 0, 0, comma 0. All right, 0 force means 0 displacement. That makes finding slope so much easier than finding 2 little points. Also, some of you are finding points that are way too close to each other. That leads to error, all right? Just saying. So try to find one as far away as you can. This looks like a likely candidate here because it's kind of like on the little crosshairs, and I could probably figure out what that is. So it goes 0.2, 0.4, so the one in between is going to be 0.3, and it went up to, well, between 8 and 10 is going to be 9. So I can use that. And remember, slope, well, first of all, I'm going to write this down here to find slope. Okay, that's what you got to do. Slope is y2 minus y1 divided by x2 minus x1. It's on your equation sheet. And so my y is going to be 9, and we should include the units because it's not just 9 anything. So 9 newtons minus 0 divided by 0.3 meters minus 0. And that gives me an answer of, when I put that in a calculator, 30 newtons per meter. Literally, it means it takes 30 newtons of force to stretch this thing 1 meter. So my answer is D. All right. Yep, there you go. No questions yet. Very good. All right, you're just soaking it all in. That's all good. It's all good. And don't worry, I don't blame you, but the option is always there. Okay, a spring that is stretched. Let me just take a little sip here. Talking a lot. A spring that is stretched, D, stores X energy. All right, I'm just using variables, right? Like almost like algebra, because it is kind of algebra. How much energy is stored if the spring is stretched to 2D, 2 times the distance? All right. Well, how do we figure that out? How do we figure any of these questions out? Start by looking at the equation. The equation is going to help you. The energy equation for a spring. All right. Be careful. This is not the energy equation. Okay. That's literally force. Okay. I've seen some of you guys do that. Like, don't look at that equation unless they're talking about force. The energy equation is elastic potential energy is 1/2 kd squared. 1/2 of the spring constant times the displacement squared. All right. And that's another strategy I'm just going to point out here. I do it too sometimes, but try to avoid saying just the letters. 1/2 kd squared is meaningless. It means nothing. But if you say the elastic potential energy is equal to 1/2 of the spring constant times the displacement squared, now you're talking like in English, and you're saying things that mean something to people. So doing that will really help you a lot, because now we know, like, hey, we've kind of seen a question like this before when we were talking about kinetic energy. We got it written out. Distance is squared. Displacement squared. That means that if I double it, 2 squared is 4. So my answer will be 4 times as much energy. So that's how you do it, okay? Look at the equation, and that will really help you figure it out. Because guess what? I'm guessing that some of you would choose 2 times because it's like double the distance. There's a 2 there, so it must be double. You're like, I don't know. And that's a reasonable choice. It really is. until you look at the equation. And then you're like, ooh, wait. All right, so look at the equation. It really will help you. Look at that. 5.3, conservation of energy. So up to this point, that was the first couple units. At least in my class, we did a quiz on that together. So go back and look at that. That'll help you too. This is the last part, conservation of energy, kind of a big deal. In physics, the idea is that energy is always conserved if, remember the if, there are no external forces doing work. Okay, most of the practice problems say to ignore friction, ignore air resistance and all that good stuff. And that means we're basically ignoring any external work. In other words, energy will always be conserved in those systems. In real life, energy is lost because almost all the time there's going to be air resistance and or friction. And friction is an outside external force. It is doing work. Remember what work is? Work is the act of adding energy to a system or taking it away. And so friction takes it away. So that's conservation of energy. Energy is always conserved in a system as long as there's no external factors, no external work being done, no external forces. So we got a kid sliding down a frictionless hill. There's our fun little F word that we like to use in physics, frictionless hill. Which of the following graphs represents the energy of the kid when he is at the top? All right, this is probably not too tough for you if you've been paying attention at all. At the top of the hill, hasn't started moving yet. What kind of energy will they have? So this is what you do. You go through the little checklist. Does the kid have kinetic energy? No. Does the kid have gravitational potential energy? Yes. Does the kid have elastic potential energy? No, there's no springs involved. Does the total mechanical energy make sense with the others? Is it going to add up to be correct? Is it not? Yeah, well, yeah, it's fine because this one lone bar graph over here goes up to this bar, and there it is, right? Like the total of the three. I think we found our answer already because literally this is the only one. This is let's make sure. Okay, nope, the kid has no kinetic energy, so we can't choose that one. Same thing with this one. This one, the kid should have gravitational potential energy, but it's not represented in this graph, so it can't be this one either. Same thing kind of here. It never says the kid is moving at the top of a hill, so this can't be it. So anyway, our choice is A because the kid has just potential energy, gravitational potential energy at the top of the hill. So that's what you got to do for these types of questions. Ooh, okay, let's look at this one. I'll show you again. Go through, little checklist. What does the kid have? The kid sleds down a frictionless hill. Which of the following graphs represents the energy when he is at the bottom of the hill? All right, now just remember, keep it simple. Starts at the top of the hill, sleds to the bottom. Okay, remember, it's not a kid on a sled, it's an object. Okay, so the object starts at the top and slides down to the bottom. It's just like Energy Skate Park, where what happened? All the potential energy that the kid had at the top is now turned into kinetic energy at the bottom. So right away, we know that this one cannot be it because it should have kinetic energy. Maybe this one, except kinetic energy, it still has potential energy, and it says it's at the bottom. We have defined this bottom, just typically this is going to be the height is 0. So if the kid is at the bottom, that means the kid has no potential energy at all. No gravitational potential energy. And there's no elastic potential energy because there's no springs either, so that's not going to make sense. So this one can't be it. Ooh, this one might be it. Kid's got kinetic energy, no potential. Yeah, this is good. And we have a winner. All right. Choice is D. See what I did? Just go through. And what does the kid have? Ooh, halfway. Okay, the kid slides down a frictionless hill. Same problem. Which of the following graphs represents the energy of the kid when he is more than halfway down the hill? All right, so let me draw my little thing again. And one thing I will say, drawings absolutely help. So it says more than halfway down. So let's just say right about here. The kid is more than halfway down the hill. He's moving down the hill, but he still has some height, right? Because here is my height equals 0. So the kid still has some height, but the kid is definitely moving more than halfway down. Well, this one doesn't make sense because the kid should have some kinetic energy. Maybe this one? We'll keep an eye on that one. This looks like half and half. So if the kid was halfway down, then I would choose this. But the kid is not halfway down, so it's not C. Letter D, the kid should have some potential energy, so it's not going to be that one. Letter E, it looks like the kid has some kinetic energy and a little bit of potential energy. This looks like the kid might be at near the top. Top. Let's just do that. We'll just call that an exclamation point. Near the top. And so the kid has like a very little kinetic energy and lots of potential energy. So our answer is going to be B, because near the bottom, it's going to be going really fast. He's not going to have a lot of potential energy, but he's still going to have some. Got it? All right. Kid slides down a hill. There is some friction. But she has fun and is going pretty fast at the bottom. Which of the following graphs best represent the energy of the kid? Okay, slightly changed. Now there is some work being done. There's some external forces happening here. And so the graph, these graphs are kind of crazy. You'll see these represented all sorts of ways. This is just one way where you'll see work represented like that, work X'd. That just means external work is being done. And I don't know, it just it should make sense to you. So let's see if it does. Kinetic energy, you know what that is. PEG, you know what that is. PEE, elastic potential energy, you know what that is. And there's this WX. That just means work, external work being done. And it also says this is initial. This is final. All right. So in other words, kid at the top of a hill, she's up here to start with. She is not moving, so V is equal to 0. And then in the final situation, she is down here. She's got 0 height, so H equals 0. But she has a velocity. Velocity is greater than 0. There was some friction along the way. So let's see which one best represents this. Well, this one looks promising, where she starts out with some gravitational potential energy at the top. Excellent. She ends with kinetic energy, yes. Oh, wait, she should not have gravitational potential energy. Plus, look at this work. What is this? This is no, okay? This is positive work. Friction doesn't add energy. That doesn't work like that. I get it work. That doesn't happen. So that's that could be a clue. You're looking for something where so right away, that means this is not going to be it either. Friction does not do positive work. It does not add energy. It only takes away energy. So we're looking at one of these two. Right away, we could tell the kid is not initially starting with kinetic energy. So we can ignore where that one's gone. So letter D is our last hope. The kid does start with potential energy. And there is external work taking away energy, the friction. And look at this. The kid ends up with kinetic energy. And look at, she lost a little bit of energy here. Excuse me. And that little bit of energy that she lost is equal to the external work that was done. D is our answer. She starts out at the top of the hill with this much energy. She loses 2 little bars of energy due to friction, which means that these little two bars of energy are not there, and she's at the bottom of the hill with a bunch of kinetic energy. Okay? Yeah. Okay, we're getting to the end. A few more questions. So a 54 kilogram kid on a 10 meter hill has 5,300 joules of potential energy and 700 joules of kinetic energy. What is the kid's total mechanical energy? Watch out. Total mechanical energy is the sum of all the energies. And it gives you a bunch of numbers that you don't need, okay? This is where being like, hey, wait, J, that's joules, that's energy. And it even says potential energy, kinetic energy. Wait, all I got to do is add 5,300 joules plus 700 joules, and that's going to be my total energy. That's it. That's all you got to do. Look at that. Okay, just being watchful of that will help you. A kid is a 54 kilogram kid is on a 10-meter hill, has that much joules of potential energy and 700 joules of kinetic energy. What is the kid's total mechanical energy when he is halfway down the hill? Ew. Wait a minute. You remember this one. The total mechanical energy does not change unless there's work being done. Since it doesn't mention work, we're just going to assume that there's no friction and all that at this point. So what was it before? It was 6,000. Well, guess what? It's still going to be 6,000. It's still going to be 5,300 plus 700 joules. Nothing's changed. Okay. Good. All right. What else we got? Hey, that looks similar. Yep. Same kid, same question. Well, slightly different question. In this case, at the bottom of the hill, what is the kid's total mechanical energy? This is getting ridiculous. I like it. These are easy questions. What is the kid's total mechanical energy? If you knew it before, guess what? It doesn't change. Doesn't change. All right. So the answer is still 6,000 joules. Okay. Doesn't change. Okay, it doesn't matter if they're halfway down, a quarter of the way down, 3/4 of the way down, 5/8 of the way down. The total does not change. All right. So you saw a similar question like that on a practice problem where there was like a loop-de-loop or something like that, and you knew that the roller coaster had a certain amount of energy up here. The total mechanical energy here is equal to the total. It's the same total mechanical energy anywhere along the path. It's all going to be the same. No matter where you are on this roller coaster, it's the same total mechanical energy. Never changes. Okay, then we get to the real math. It's like, what's his speed? What's the kid's speed? You know what you got to do here, right? Bottom of the hill. What's the kid's speed? All right. Bottom of the hill, what kind of energy does the kid have? Well, all that potential energy, the total mechanical energy is equal to kinetic energy plus gravitational potential energy plus elastic potential energy. Now, you know, at the bottom of the hill, the kid is not going to have gravitational potential energy and there's no springs involved. So that means that the kinetic energy of the kid is equal to 6,000 joules, as we've already established. It also means you have to take the kinetic energy equation, 1/2 mv squared, and you have to solve for velocity. So what I'm going to do is I'm going to multiply both sides by 2, and it's the last time I'm going to work through this for you. Okay, that's going to cancel out the half on the one side. And now I'm going to divide both sides by mass. That will cancel that out over there. Divide that there. And now I've got velocity squared is 2 times the kinetic energy divided by the mass. And since we can't leave it as squared, we have to square root both sides, which means that velocity is equal to the square root of 2 times the kinetic energy divided by the mass. Now this is where you got to make sure you practice with your calculator. Use the calculator, it's going to work for you. If you're not sure, put parentheses at the beginning and at the end in your calculator, and that will get it for you. All right. And when you put those numbers in your calculator, it ends up being, let's see, velocity will be 2 times the kinetic energy, which was 6,000 joules, divided by the kid's mass, 54 kilograms. And like I said, put a parenthesis at the beginning and the end if you're not sure. And when you do that, the answer you get is 14.9 meters per second. All right. Practice, practice, practice. There's plenty of practice problems that involve that. If you're not sure, ask ChatGPT or something to make some questions like that and see if you can solve them, okay? For real. Okay. Which frictionless ramp will give the ball the greatest speed at the bottom? If you were there this day, you might remember I asked a very similar question. I was able to show you with some marbles and some ramps. The bottom line is, wait for it. Which one is it? They're all the same. Okay. The reason they're all the same is because they all end at the same point and they all start at the same height. And so because it's the same marble, same mass, what is that supposed to be? I don't know. Gravitational potential energy, I think it was supposed to be a big G, is mass times gravity times height. And since mass and gravity are the same and height's the same, that means they're all going to start with the same gravitational potential energy, which means at the bottom of the hill, they're going to have the same kinetic energy. It doesn't matter which path they take. Now, which one's going to get there first? A will get there first because they all had the same speed in the end, but A gets to that top speed the first. It gets that speed first. C will be the last one to get there because it's the last one to get up to top speed. It's going to spend, C will spend half its time, dope going slow over here. All right. By the time it gets to the part where it starts to speed up, A is probably already done. But C will eventually get to the same speed because it drops down to the same height. Okay. Same. Okay. We have a situation here. What is the minimum distance required to push the 12 kilogram ball with 175 newtons of force so it rolls up to the top of the 2.2 meter hill? Assume no friction. That's good because friction will really mess us up a little bit here. Now, I'll say this is probably one of the more difficult types of questions you may or may not see. All right, this is where you really got to know your stuff. And what you need to know is that the total mechanical energy at the bottom, we'll say, is equal to the total mechanical energy at the top. All right. In other words, the kinetic energy plus gravitational potential energy plus elastic potential energy at the top, at the bottom, is equal to the kinetic energy plus the gravitational potential energy plus the elastic potential energy at the top. Now, at the bottom, the ball is going to have nothing but kinetic energy. It is not going to have gravitational potential energy at the bottom. It is not going to have elastic potential energy anywhere because there's no springs involved. At the very top, you just got to get up there, right? So you don't need it to keep going. You need the minimum amount of energy, the minimum amount of distance. So you just want to just barely get up there. You don't care about it keeping moving. So it's not going to have any kinetic. You don't need any kinetic energy. We keep it zero. It just needs to get to the top. It's going to have nothing but potential energy, gravitational potential energy, but it's not going to have any gravitational potential energy. So what that means is that the kinetic energy at the bottom, 1/2 mv squared, will be equal to the gravitational potential energy at the top, mass times gravity times height. Okay. So then I could just start plugging in numbers. Well, what am I trying to do? What is the minimum distance? Wait a minute. What? Minimum distance. Okay. So you're gonna be like, well, what am I trying to find here? Let's just do this. We don't need velocity. We trying to find velocity? No. Okay, so that happens sometimes. We took a wrong path, and you know what? That's okay. It made sense, and then what happened, and I'm just doing this to illustrate that sometimes we kind of lose track of what we were supposed to do here. We don't need to solve for velocity. We need to solve for distance. Wait, there's only one equation that we have that solves for distance, and that is work is force times distance. And look at, wait, what is this? We have force right here. Like it even says of force. And we weren't paying attention. We just went ahead. But that's okay. It's still going to be the same principle is going to still apply here. Because what else is work? Work is also equal to the change in energy. Oh, well, we're talking about energy, right? What kind of energy? Gravitational potential energy. Wait, we're still good. We're still good, right? PEG. So in other words, you see what I did there? I mean, just to recap here, the force times the displacement is equal to work. Why do I need that? Because I'm literally trying to find the distance, the displacement, okay, of the ball. So I wrote that down. I'm like, there's only really one equation that uses displacement in this way. The spring equation, that does not going to apply. All right, let's do the work. Oh, work is also equal to change in energy. So like I could set these two equal to each other, and like, we know this. And so it's like, well, that's mass times gravity times height. We do know all those. So let's try this out. Force is equal, let's not skip ahead here. Force is equal to mass times gravity times height. And so I want to try to find the amount of distance. So distance is mass times gravity times height divided by force. Okay, now at this point, I probably have lost a bunch of you. You're gonna have to rewind this and maybe watch it again. Maybe ask me in person or something if you have any questions, and that's okay. Just go through it and go slow. You know, I did explain in all the steps. Remember, this part here was sort of a dead end, and you might find yourself in a dead end sometimes. It happens. So distance, yeah, let's also put that out. The distance is gonna be the mass, so 12 kilogram, times gravity, 9.8 meters per second squared, times the height, 2.2 meters, divided by the force, 175 newtons. When I put all that into my calculator and I solve it, it seems like we have to push it for 1.5 meters. All right, now that's a big one. Like I said, you might need to rewind and go look at that, but it's all about just knowing that the amount of energy that changed is equal to the work done. Remember, because that's the definition of work, energy changing. And how much energy did it need to change? The amount of energy that the ball gained or will gain when it gets to the top of the hill. Okay, that's how much energy does it have up there. Okay, that's the thought process there. Rewind it if you need to. Where is kinetic energy? Thanks for asking that. That's a great question. So what you can do, there is another route to get this. Okay, all right, yeah. Just to really quick explain, you could find the kinetic energy at the bottom. Okay, like whatever. Here, let's try this. Find the amount of potential energy at the top. So the potential energy at the top up here, and I'm just, bear with me here. That will equal the kinetic energy down here, right? Those will be equal to each other. Where did it get this kinetic energy? You had to do work on it. You had to apply a force. You had to add energy to it. So the kinetic energy is actually equal to the work done. Okay, so that's another way to think about it. There's lots of ways to think about it. This will honestly probably be the last question I do. Okay, this one is similar to the lab that we did in class, and it's a very common lab. So we got a Hot Wheels car released from rest from the top of a frictionless track. So here, like, we put our car, that's my badly drawn car, and it's going to go down this ramp. Okay, that should look familiar. If not, it's pretty straightforward. At the bottom, so this is a little bit different than the lab we did, but at the bottom, the car runs into a pencil. Somebody left it on the track, right? And the car keeps going. It smashes into the pencil, and the pencil kind of pushes on it slows the car down to a stop, right? So can you picture that? Car's going down the track. It gets to the bottom. Somebody left the pencil there, and the pencil stops it. Not instantaneously. It slides a little bit, and it stops. So at the bottom, and this again is one of those more difficult questions, but that's okay. Like, you know, you do what you can with this. I'm not saying ignore it, but it's okay if you need to rewind this and watch it again. So the pencil applies 0.57 newtons of force to the car. Okay. The car has a mass of 0.034 kilograms, and it started at 0.85 meters off the table. How far does the car go before it stops? Okay, let me redraw this ramp a little bit. It's going to look something like this. You're going to have the pencil right there, and the car will start here. It's going to go down the ramp and hit the pencil, and then it's going to slide to a stop. Got it? So what you can do, or look to do, it seems like we could probably find what kind of energy does it have up here? Gravitational potential, right? What kind of energy does it have at the bottom of the track? Kinetic. What's happening here? The pencil is slowing it down. In other words, the pencil is changing the energy. It's doing work. Whoa, what happened to my W? I just got all excited about that W. Let me erase that because that is kind of a silly little W. Let's try not to ruin things here. Click. I don't know what's going on. I guess I'm getting tired. All right. So that should be work. So at the top, it's got potential energy, gravity, turns into kinetic energy at the bottom. And then at the bottom, it hits that pencil. So here's our little pencil friend here that somebody left. And it drags the car to a stop, removing the energy, AKA doing work. Okay, well, let's start by maybe, there's a lot of ways you could do this, guys. I'm gonna do sort of like the brute force, like kind of work our way slowly through it method. Let's find our potential energy at the top. Maybe mass times gravity times height, right? Let's see if we got all that. Mass, yep, 0.034 kilograms. Gravity, 9.8 meters per second squared. The height, ooh, good, we got this, 0.85 meters. And I actually don't remember that one. I don't have that one pre-written down, so 0.034 times 9.8 times 0.85. I get 0.28322. I'm not going to remember. That's too many numbers for me to remember at this time of night. 0. My light is not good, so 0.28322 joules. Now you might be like, Mr. Junior, can we round that? Sure. I just don't recommend rounding until the very end, so it's not that many numbers to write down. And so I'm going to keep it there until we get to the end. So that's how much energy it has at the top. So we now have this. So guess what? All that energy turned into kinetic energy. Where'd my mouse go? There it is. So now kinetic energy. So the kinetic energy will also be equal to 0.28322 joules. Okay, at the bottom. That's right before it hits the pencil. Okay, so the car has this much energy at the bottom. Do you follow me? You don't have to solve for velocity at this point unless you know you want to. You could solve for velocity because if I wanted to solve for velocity, I'd just do the square root problem thing. But that's not what I need for here. Now I know that that energy, the pencil takes all that away. The pencil takes away that energy. In other words, it does work. Okay? It does work. It takes away that energy. In other words, work is equal to the change in energy. That's on the equation sheet. What is work? Ooh, there's another equation that involves work, the very first one. Force times displacement. And guess what we're trying to find here? We are trying to find how far does the car go before it stops? That's displacement. That's what we're trying to find. So displacement, if I rearrange this and divide both sides, is going to be work divided by force. My work is exactly how much energy I lost. So 0.28322 joules. Look at how I'm getting excited. I'm writing diagonally. Divided by the force. The force is 0.57 newtons. And hopefully when I put that in my calculator, it's one of the choices. So divided by 0.57, I get 0.49887. 0.4, I'll write that here somewhere. 0.4988. It ends up being meters. So that is my final-ish answer. The closest one to that is C. Okay. Again, it's nothing you can't handle. It just takes a little bit of thought and process there. So that's essentially it. I'll leave that out there for a moment. But really, I'm going to wait a moment here and just, does anybody have any questions I can answer? Got a glass of tea here. How do you know what number in this? How do you know What number is the spring constant in a question? Great question. Let me see if I go back a little bit. Did I ask any questions about springs? Not recently. Nope, 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 not really. Let's see, massacre. All right, tell you what, let's do this. Get back to that last question. Whoa, 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 whoa. Uh-oh. Well, I just closed the live stream. Let's do this. Let's not make that same mistake again. Okay, that is a great question. And I apologize, I got a little faux pas going on here. I messed things up. Let's take a look at, so here's the review guide, right? How do you know? So let's look at a question. Okay, so here's one. Let me just zoom in a little bit here. How much energy, the quick answer to that question is usually it'll just tell you pretty much straight out. Like for example, this one says it has a spring constant of 40 newtons per meter. This one has a spring constant of 40 meters per, okay, I was asking force and energy. This one has a K value of 20 newtons per meter. Okay, so most of the times it'll say something like that. Now the real trick is newtons per meter. Whenever you see newtons per meter, that's the spring constant. Okay, sometimes it'll call it the K value, literally, because that's the K in the equation. But so in this one asks it like twice in both ways. So that's how you know. Okay, and as you can see, if you did the review guide, a lot of these questions aren't going to be like, that's not our favorite topic, but it is something that's brought up in there. So great question. Anything else? So to repeat myself, it'll usually just say spring constant or it'll say K value. And it will definitely say newtons per meter. Okay. Anything else? All right. Well, thank you for joining me. I hope this was helpful. If it wasn't, well, it's kind of fun, kind of, sort of. Let me know if you got any questions. Like I said, there's a lot of tools out there you can look for. You got online tutors. I showed you today how you can use possibly, AI, ChatGPT or something like that to help you with that. You can always ask me questions or each other, send me messages, send me emails. We've got a few days for this. As long as you're not watching this on Sunday night or Monday morning, you should be good. So, all right, I'm going to end this. You guys have a wonderful evening, and I'll see you when I see you.